This meeting is being recorded.
Okay, good afternoon, everyone. Let's just start. So I don't know if any of you saw, but short while ago, we released problem set number 1. So you'll see it on Piazza. The link is out here, which actually basically takes you to a Google Doc where there are some instructions and then the actual link to a Google form, which is where, much like the discussion sections, you are going to get your personalized copy of the PSET. It's personalized in the sense that we changed the data underlying the problems, but the problems are otherwise the same. So like, for example, the expression we may give or the truth table we may give would be different, and also the problems are shuffled. So those are the changes. So yeah, it's in our attempt to make sure that you do your own work. The PSET itself, so after you get your customized copy, in case you don't receive it, contact us on Piazza and we'll manually send you the one. So we record what we are sending to you so that when we auto-grade, it is graded against that. So exchanging with other students is really going to fetch you a close to 0 score. The assignment itself is in the form of a notebook. So when you get this IPyNB file, probably the easiest thing is to upload it to your Google Colab folder and then open it there. And you will see kind of the problems there, and then you're going to fill the answers. It's super important that you follow very precisely the instructions for the formatting of your answers. So like, just to give you an example, like when it says only use certain operators, you must make sure only to use those operators, and so on and so forth. Sometimes it will ask you to give the answer in a list, square bracket, comma, separated elements. This is again because that's what the autograder expects. So please don't vary from that. Just to make sure that you don't run into any problems relating to this. So what we are doing is we are going to give you 2 attempts at uploading. So the first time you upload, in case you get some zeros on the problems, then you have a second chance. The system actually will not prevent you from uploading more than twice. I think the autograder really, if we have our act together, will give you a score of 0 from 3rd attempt onwards. But don't worry, we are going to just take your second attempt. Okay, in case you have 2 attempts, in case you have 1 attempt, then this is just the first attempt. So anyway, these are problems. Most of them have already been covered in the lecture. Other than, I think there is one problem which relates to these things called Karnaugh maps, which we are going to cover today. The problem set itself is also released on Gradescope now. So you will see PSET here. It's due basically 3:50 p.m. next Monday. Those of you who want to avail of your late days, there are 3 late days that you can use against your quota, but I really strongly recommend not to waste your late day quota on this early PSET, because latter PSETs and design assignments are going to be, relatively speaking, harder. And if you run out of your quota, you run out of your quota. So the other thing to remember is that even 1 second delay means that you're using up a whole day at that point. So be judicious about it. Maybe it may be better to, if you're just running short on one question or something, maybe it's better to let go and not waste your late day. But of course, it's your choice how you want to do it. So anyway, it's on Piazza. Kind of the link. Then the link takes you to the form. The form sends you the customized thing, and then then when you are ready, you upload. The autograder grades against the customized version that we have created for you. This is something we are trying out new this time around. I think kind of got let's say concerned about potential honor code violation we were seeing, and instead of chasing to the campus every time, I felt it's better to try to prevent it. So don't copy answers, because answers are going to be different. Okay, so any questions before I switch to the main lecture? Okay, so if not, let's no, you won't have a quiz next week, and I really urge you to please speak up. It's very hard for me to monitor the chat during Zoom in a large lecture like this, so just blurt out your question orally, please. No, not quiz next week. We are going to give, it will be, in all likelihood, will be the week after next. Okay. And as promised, I'll always give you a week's notice in advance. Any other question? Okay.
Oh, excuse me.
Please, yeah, go ahead.
Yeah. When I click on the link in the Piazza for the PSAT, it says like and you request an access to it. Should I switch?
You are logged in as your UCLA account, right?
Yes. Oh, never mind. Right now it's working. Never mind. Right now it's working. Okay. Sorry.
Okay. Yeah, it should work. It should work. Or at least, yeah. Unfortunately, for some of these things, what happens is my TA and I also are the owners, so we are not always detecting problems. But I'm glad it's working. Just fill out the form. See if everything ought to work. Okay. Any questions? Okay. If not, let me start the main lecture. Okay. Okay, awesome. So last time we were looking at various ways in which we represent Boolean functions, and towards the very end, so we had talked about expressions, truth tables, and so on and so forth. But and we had talked prior to that, we had talked about concepts like min-term, max-term, and so on and so forth. But there's one particular representation which is kind of pretty powerful in the sense that it lets us optimize the implementation of Boolean functions. Remember, we had talked about how to merge rows in a truth table so that we have more compact representation. It lets us do that, and we were discussing at the very end, which is this cube-like notation where a Boolean function is represented. So you can think of inputs, which are the rows of the truth table, correspond to points in an n-dimensional space. So in this case, it's a 3-input function. So we have 3 dimensions, and so you can think of 8 possible points. So there's 8 possible corners of the cube, and then each corner corresponds to a potential min-term, but the function is 1 at only some of those points, right? Some of the points in the input space, the function takes the value 1, some of them it takes the value 0, and some of them, as we saw some time ago, the value may not be defined. It's a don't care. In this picture, the blue bubbles indicate where the function is 1. So in our min-term notation, is basically saying mitnul 1, 2, 3, 5, 7 is where the function is 1, and those are the 5 things out here. So main thing to note out here is that in this cube-like notation, if I look at an edge, then on that edge, 2 of the variables, in this case 2 out of 3, have the same value, and the third variable has a different value. So if, for example, I look at this and this, then the middle variable, which is the variable b, is the one which is changing. So between the two nodes connected by an edge, they differ in one variable. In other words, we are basically saying that in this case, both of them are blue. So the function is 1 in both of them. And we are basically saying that the first variable is 1, the third variable is 1, the middle one, I don't care because it could be 0 or 1. So this allows us to merge things. And we had discussed that at the very end. So the way the intuition works is that we merge minterms into edges. So if two minterms, which are painted blue, indicating that they are 1, in software, obviously, we'll have some data structure to maintain it. Then we merge them into smaller term, because instead of 2 terms with 3 variables each, right, each minterm is like an AND gate, right? So instead of 2 AND gates of 3 inputs each, if I merge this, then I end up with a 1 AND gate with 2 inputs, right? Only the inputs A and C matter, B is don't care. And we can play the same game with all the other edges which are connecting two nodes with value 1. But we can go further. And that's what we had discussed last time. We can merge edges into faces. So if I look at the face, which is out here, in that face, if you see, middle variable doesn't matter. And also the first variable doesn't matter, because the first variable is also taking all possible values. So the only variable that matters is the third variable, which is A, because we are really using this CBA notation. So A equal to 1. So if I were to think of what does this face represent, this face represents all those points where A is equal to 1. And so now, instead of, originally we had started out with 4 minterms, that means 4 AND gates with 3 inputs each. And now we basically eliminated everything and we are just left with a wire A, right? That's it. So, and we can play this game in more complicated function. We may be, the n-dimensional space may be like, if I have 100 inputs, then I'm dealing with a 100-dimensional space. So you have, I can merge faces into 3D cubes into 4D cubes, and so on and so forth, depending upon whether all their corners are, all the corners are such that function has a value 1. So in this particular case, after we play this merging game, the face becomes A. So that's noted by XX1. X is saying doesn't matter. So C doesn't matter, B doesn't matter, C, A is 1. And then this particular edge here, A is changing. So A doesn't matter. B is 1 and C is 0. So it is 0, 1, X. And so the expression becomes A, not C and B. Whereas originally we had 5 minterms. 5 minterms would have meant 5 AND gates with 3 inputs, 5 AND gates. This is a typo. There should not be a D out here. Okay, 5 AND gates for 3 inputs each, and then feeding them into an OR gate with 5 inputs. Here, I have 1 AND gate with 2 input and 1 AND gate, 1 OR gate with 2 inputs. So much, much cheaper implementation. And that's the intuition. Now, these are toy problems. In real life, your combinational circuits have many, many tens or hundreds or even thousands of inputs. And so the gains that one can potentially obtain there are tremendous. But at the same time, the problem is also a lot harder because you're dealing with very high dimensional spaces. And that is where other type of methods, other type of representations, not just cube, also get used. So this is kind of the basic idea. But what if our function had 4 inputs, 5 inputs? Okay, so remember, before these design tools emerged in like 1980s, 1990s, before that, people used to do this stuff by hand. So a lot of techniques got developed which would help humans do more complicated systems than just 3 inputs with this. So 4 or 5 inputs kind of things people were trying to do by hand. So methods were developed which would still allow humans to do this kind of design, but with, let's say, 5 or 6 inputs, up to that complexity. And we'll see very rapidly, very soon today, one of them called Carnot maps. But I could, essentially with the cube approach, we kind of run into this problem of drawing a high dimensional space on a flat paper. Even 3D was hard, right? We were drawing, kind of going into the paper. Imagine if I were a function with 4 inputs, then I will have to draw a 4D hypercube. I could still do it. It's like one 3D cube inside an outer 3D cube. So this dimension is kind of indicating the 4th dimension. So I can play some clever tricks, but soon, as you can see, it soon gets very messy. Apropos this function, this is our good old prime or 1 function, right? So 4 input, if the 4 inputs either represent 1 or a prime number, then we want the output to be 1. So that's what we see out here. And in this case, the inner cube is our original 3D 3-input function, right? We see the face here, and we see that edge out here, but now we also have some additional edges. And again, I can merge these things to create a, so that's the merging game we are doing. So there is a face and 3 edges. So if I show this thing to you, a face and 3 edges, what do you think would be what kind of gates would I need? So each edge is, in this particular case, 0, 0, 1x. To implement 0, 0, 1x, what would I need? So let's start with, to implement the minterm corresponding to 1, 1, 0, 1, which is D is high, C is high, B is low, and A is high. What would I have needed for this midterm? I would have needed what kind of gate? What is the form of a midterm?
Distributed normal form?
Say it again. It is what?
Disjoint normal form?
No. What is the form of a midterm?
Like you just add terms, so or, right?
It's an AND term. Midterm is AND, right? So each midterm represents, each corner represents an AND gate. So this represents an AND gate. But by merging each edge, one of the variable disappears, right? So originally this corner and this corner, each one of them was a midterm, but variable D in this case doesn't matter, right? This corner is 0, 1, 0, 1. This corner is 1, 1, 0, 1. So 0 and 1, which corresponds to D, they don't matter. So now I am left with a reduced term. D doesn't matter, less than X. C is high, B is 0, A is high. So I'm looking at an AND term, which is of the form C and not B and A. So now I need an AND gate with 3 inputs instead of 2 AND gates with 4 inputs. Right? Each minterm would need, it's an AND term with 4 inputs. So each minterm, normally, each minterm corresponds to an AND gate with 4 inputs, right? Because I have 4 inputs to the function. But by merging, I'm eliminating one or more of those inputs. So each edge, I eliminate 1. Each face, I eliminate 2. Each 3D cube, I eliminate 3, and so on and so forth. So that merging reduces the size of AND gates and also reduces the size of the OR gate that those minterms are combined by. This is an OR term, right? So if I were to naively implement this, I would need 1, 2, 3, 4, 5, 6, 7 minterms with 4 inputs each. So I will need 7 AND gates of 4 input each. And then I will have to combine these minterms, right? So I will need an OR gate, which will have 7 inputs and 1 of those, right? That's what I would need. 7 gates of 4 input and 1 gate of 7 input. That's what this implementation would have looked like. And some NOT gates, right? So I'm ignoring the NOT gates out here. But by merging, I have 1 face and 3 edges. So face is 0xx1. So what kind of gate would I need for that?
Still AND gate,
It's still AND gate, and how many inputs?
2 input.
2 input, right? So this is an AND 2. So I need, so with the new implementation, I need 1 2-input AND gate, 1 AND gate of 2 input. Then I have 3 edges. So how many, what kind of gate would this edge need?
3 input.
3 input. And how many of them? Well, I have 3 such edges, right? 3 pink colored things. So I need 3. And then I need to merge all of them together into an OR gate. How many? What kind of OR gate will I need? How many product terms? How many product terms? 4 input. Yeah, exactly. So I'll need. So this is what I will need. The first number here is the number of gates, and the second number is the number of input. So I need 1 AND gate with 2 input, 3 AND gates with 3 input, and 1 AND gate with 4 inputs. And then again, I need NOT gates for each one of the A, B, C, D, right? So generally, probably all of them occur in this thing. Okay, so if I count the total number of things, so I need 7 times 4, 28, plus 1, 7, plus maybe 4 NOT gates. So my original design would have been 28 plus 7 plus 4, 39 cost. Whereas this one, I need 4 NOT gates. So the cost here would be 2 plus 9, that's 11, plus 4, 15, plus 4, 19. So the cost here would be 19. So significant reduction, roughly factor of 2 reduction in the cost that we have with playing with this merging game. And that's kind of thing. In bigger design, the gains are even more because you have more like typically functions in real life, not everything depends on everything. There's a lot more room to play with. Okay, so that's the idea. So we kind of end up with this. So you can see, right? I mean, this term is the face, 2 inputs, and the other 3 terms are the edges, right? Sorry. Yeah. So the other 3 terms represent the edges. So that's the cube-based approach. Now, as you can see, if I attempted to do a 5-input function, 6-input function, we'll probably begin to struggle. But 4 we can certainly do. And still kind of drawing is messy, you know. So there is a approach called Karnaugh maps, which you can think of it as a way to draw the cubes nicely on a flat piece of paper. That's really what Karnaugh maps are. So what does that mean? Okay, so let's work on that. So it's a method for simplifying Boolean expression, but we write them as tables, but not like truth tables, because in truth tables, the problem was it's very hard to figure out which rows can be merged because they may be non-neighboring rows. So this is a way to write tables, but these are 2D tables such that we can figure out merging opportunities easily. So the way it works is the following. We write it as a 2-dimensional table, and inputs, so in this case, it's a 2-bit function. One input is A, the other input is B. So we write some inputs to correspond to columns and some inputs to correspond to rows. In this case, I have just 2 inputs, A and B. So A represents the columns and B represents the rows. A can take 2 values because a single thing. So one column corresponds to A equal to 0, the other corresponds to A equal to 1. And likewise, B can take 2 values. So B equal to 0, B equal to 1. And then in the squares, we fill out the values. So these little numbers that you are seeing, 0, 1, 2, 3, that is basically representing the square number, the ID of the square. And the ID of the square is really the min-term number. So we kind of think of it as BA. So BA in the top left square is 0, 0, so that's number 0. In the square out here, it is 0, 1, so square number 1. 1, 0, so that's square number 2, square number 3. That's exactly your min term numbers. So this thing is really your min term number. Okay, so the main thing is that you should think of this table to be such that, and we'll shortly see that as we move between one row to another row in the same column, or one column to another column in the same row, only one of the inputs should change value. So right now, of course, there is only one input, so it's tautological. So that's one requirement. Only one input changes value. And the other one is that you really need to think of this table as kind of a wraparound. That is, if I'm in this cell, and if I move right, then I go to this cell. If I'm in this cell, if I move right, I jump back out here. So there's a wraparound. And likewise, if I'm in this cell out here and I go down, then I wrap around. So think of this table as kind of wrapping around through some interdimensional space, okay? And we'll shortly see that these two things are the power of Karnaugh map. So let's think of a 3-bit function. So let's say I have a 3-bit function which takes input C, B, and A. So we have C and B out here, and I have A out here. So again, columns, since they're a single input, 2 values, 0 and 1. CB can take 2 values, right? 2-bit values. So 0, 0, 0, 1, 1, 0, 1, 1. But this is where our first rule comes in. I have to assign values to the rows such that moving from one row to next row will change only 1 bit. So we do it 0, 0, 0, 1, but then after 0, 1, instead of going to 1, 0, because 0, 1 to 1, 0 means 2 bits will change, I actually go to 1, 1. And then from 1, 1, I go to 0, 1. And if I wrap around, right, if I go back out here from 0, 1, from 1, 0, I'll be back to 0, 0. So every time I'm moving down or up the column or wrapping around, only one of C or B is changing. And that's the coding. What is this coding called? We have seen it in the discussion sections. Like when neighboring values change only 1 bit. Okay, I'll leave you guys to figure it out what it is. Let's say I had numbers 1, 2, 3, 4, right? I mean, normal binary code when we assign it, right? That's 2-bit as base 2 numbers. There, if I move from one number to the next number, I may change multiple bits simultaneously. But this type of code has a property that, so think of like row number 0, 1, 2, 3. I'm actually labeling them such that the coding changes only 1 bit at a time. And that has a particular name. So I would like you guys to figure it out either through discussion section notes or just Google for it. Okay.
I just check my discussion notes for gray encoding.
Yeah, gray encoding, exactly. Gray encoding. Okay. It has a lot of uses, but one of the things is it allows for, in this particular case, allows for some nice properties. Okay, the other thing, if you noticed out here, is that you see this line which is drawn out here, this one, that black line under B, is basically saying that on those 2 rows, B has the value 1. And likewise, you see this line out here. It's saying on those 2 rows, C has the value 1. So it just helps draw out like which rows B has the value 1 and which rows C has the value 1. So it's very easy to see that row number 3 from the top, both B and C are high. Okay, so it kind of gives a visual reminder. It's not always drawn, but sort of oftentimes it's useful. Okay, so that's a 3-input Karnaugh map. Okay, and again, kind of it has this wraparound property. So the cube and the Karnaugh map really correspond to each other. So we previously had the 4D cube, and we have now a 4-input Karnaugh map. So in a 4-input Karnaugh map, DCBA, so DC are drawn out here, BA is drawn out here. Same property. If I'm moving from one column to next column, 0, 0, 0, 1, 1, 1, 1, 0, again gray coding, and column is gray coding. And this is highlighting where A is 1, this is highlighting where B is 1, this is highlighting where D is 1, and this is highlighting where C is 1. Okay. And now you can again label the minterm ID. So minterm number 0, 1. So the interesting thing out here is if you see minterm 0, 1, 2, 3, 4, 5, 6, 7, then we skip 8, 9, 10, 11, 12, 13, 14, 15. So they're kind of jumping around a bit. But you can see, like, why is this guy 9? Well, this is 9 because we are in 1, 0, 0, 1. So this thing corresponds to, this one corresponds to 1, 0, 0, 1, which is 9. Okay, so whatever we can do in that cube, we can do it in this 2D table.
Quick question.
Yeah, go ahead.
Could you go for the wraparounds and how they work for this like 4-bit case?
Say it again. Could I?
Like the wraparounds, how they go? How they
Oh,
work
the
for this?
wraparound, same story. So if I'm out here, I can wrap around out here. Okay, and again, you would see that if I go from here, rightmost to leftmost, I would be moving from 1, 0 to 0, 0. So only a change of 1. Only one bit is changing.
Okay, so the wraparounds are for like the inputs and not like the index you place on the inputs.
Correct.
Okay,
They are for the input values. They are for the binary coding corresponding to those little numbers I have.
All right, thank you.
Okay. And same thing you would notice, like if I were to move from here to here, same story, right? Because I was at 0, 0 here and 1, 0 here. So 1 bit changes. Okay, so whatever I can do in the cube, I can do in this flat table, and I'm sure most of us would agree that drawing this table on the right is a lot friendlier than drawing that cube on the right, on the left. So kind of the idea then is we are going to fill in the values in this. This is just repeating something I already said. Okay, so now, actually. So remember, in the cube, I had talked about I can merge two things if they are on the same edge. Well, two nodes. So each node on the cube is a cell in the Karnaugh map. Neighboring cells in the Karnaugh map correspond to nodes which are connected by edge in the cube. And that you can see because only 1 bit changes as I move from one cell to a neighboring cell. So for example, for cell number 7, it has neighbors, and you can look at those neighbors by going left, right, top, bottom. Those are the ones which differ from it in 1 bit location. In other words, they correspond to an edge. So those are merging candidates. If the function was 1 in 3 and in 7, that means 3 and 7 could be merged. If the function was 1 in 7 and also 1 in 6, that means I could merge those. Faces correspond to groups of 4. So if you think about 2, 3, 6, 7, for 2 of the variables, the value doesn't matter, right? I mean, so 2 and 3 and 6 and 7, I can say that this whole stuff corresponds to A doesn't matter because they're valid for A equal to 1 and A equal to 0, but B is 1. So for this highlighted red thing, right, B is 1, and C doesn't matter because C can take the value 0 and 1, 0 here and 1 here, but D is 0. Okay, so this whole thing is D is 0 and B is 1. And that's how we are merging them.
Quick question.
Yeah, go ahead.
So is it like any four, or does it have to be like in like a square sort of thing?
So great question. It has to be any four which form a cube. Okay, so what I mean by that is it could be like this. It could be four in a row. It could be four in a column. Also, so those are also valid.
And then like for the two case, do the wraparounds count where I can go from like in this case like index 2 to 0? Okay.
Absolutely. So for example, I can have 10, 8, 0, and 2. You can view them as a merge candidate. Right? 8 has neighbors, 8 and 10 are neighbors, right? Left, right, and 8 and 0 are neighbors. So you can think of 8, 10, 2, and 0 actually going through this whatever interdimensional space. They actually form a face there.
I
So
also have a
that's
question
the effect of the wraparound. Yeah. Go ahead, please.
about the ordering of the variables. Do we always go on the left-hand side, what is it, the first one, and on the top the last ones, or can we flip it? Or
That is a convention, but you're asking a great question because order matters, right? If I were to instead use A, D, B, C, then the Carnot map will look different. It's the same function. It's just that I've shuffled the order of the input variables, right? Conventionally, in this textbook, what they're doing is if my function takes some inputs, then the first input and the second, let's say the function takes 4 inputs, then the first and the second from the left in the function go into the column, and the third and the fourth input to the function go into the, first and second go to define the rows, and third and fourth go on to define the columns. But that's just convention. You can pick anything as long as you're consistent. Now, what we do is we will typically tell you, consider this order, because otherwise we will have a horrendous grading job, right? So we will tell you what to use. Okay.
Thank you.
Okay, so I can have entire rows, entire columns. So I can merge like this, and I can merge vertically also like that. Okay, so all those possibilities are there. So now how do I use the Carnot map? So given a function, the first thing I'll have to do is I'll have to fill in the output values. So going back to that function 1 or prime for a 4 input, I will put all the values out here. They look like this. You can check. Cell number 1, 3, 1, 2, 3, 5, 7, 11, and 13, right? Those are the ones in the primes. So I fill this thing in. And now I'm going to play the merging game. So previously we saw the merging could be done 1 face and 3 edges. Hopefully we get the same thing out here. Okay, so first we are going to try to find clusters. So we can find this cluster. That's a group of 4, and that corresponds to the face in the cube. And then I'm going to find edges. There is this edge, there is this edge, and can anyone tell me what is the third edge? Remember, we expect a third edge. So which two?
3 and 11.
3 and 11. Excellent. So that's the wraparound case, right? So 3 and 11. So that's the idea. Then we take these clusters and make implicants out of it. So implicant, if you remember, is any term which, if true, the function is true, right? So each one of these things correspond to terms which, if they are true, it's a min term is an implicant, but not all implicants are min terms. So like square number 11 corresponds to a 4 input AND gate, right? It's basically a AND expression with 4 inputs. If that expression is true, then the function is true. But let's take this red square. If this function is true, that means if it takes a true value, namely it's in one of those 4 squares, 1, 3, 5, 7, then we are saying, then also is the case the function is true. So each one of these things are an implicant, namely an expression which, if true, means the function is true. So the green one out here corresponds to, well, A doesn't matter, B is 1, as you can see from the column, and C and D are both 0. So this is B and not C and not D. The red one, B doesn't matter because B takes both 0 and 1, but A is high. So you see A, and likewise, looking at the rows, you can see C doesn't matter, but D is 0. So it's A and not D. And likewise, if I look at this one going from 5 to 5 down, A is high, B is 0. So you can read the column out here. And then it's spanning 2 rows. So D gets decimated. We are left with C. So we have a C. And for the final one, the wraparound arrow, you will see the expression is this. And so each one of these expressions have the property that if it is true, if expression is true, like if my inputs are such that A and not D is true, then that means I'm in one of those cells, right? I'm either in cell number 1 or 3 or 5 or 7, and therefore the function is true. And so to create this thing, we are just going to OR them together. So now let's visit some of those. Minterm we had talked about. Minterm is expression which is an AND expression. It has a literal corresponding to every input in the circuit. So means if I have a 4-input function, A, B, C, D, then A, B, C, D, all of them occur either as they are or complemented. Implicant is the term that I just used, is a product term, is an AND term, which if true, implies that the function is true. So, so minterms are implicants, obviously, because if minterm is true, if minterm of function corresponds to expressions, which if true, the function is true. But I can also have implicants which are combinations. So in particular, what happens is we combine things. When we are merging those corners of the cube or cells of the Karnaugh map, the game we are really playing is we are basically saying, if I have an expression like this, right? If I have 2 terms where y doesn't matter, then x and if x and y and or x and not y, if that's the expression, then that's the same thing as in x. So merging is really doing this game, okay, and it's doing it repeatedly. So that's how we create implicants. We merge minterms to create implicants which are smaller, or depends on how you define it. They're smaller in terms of Boolean expression, but they're bigger in the sense they're covering more corners or more cells in the in our cube or Karnaugh map. Prime implicant. Prime implicant is an implicant that cannot be made any larger. That is, I cannot have it fewer literals. I cannot do any merging anymore. So what do I mean by that? So if you look at, let's say 1 and 5, I could have merged those. That's an implicant, right? If I do 1 and 5 together, they correspond to an expression, which if true, the function is true. But 1 and 5 can be expanded, can be merged with 3 and 7 to make a bigger thing. So 1 and 5 would have been an implicant, but they would not be a prime implicant. So prime implicant is an implicant that cannot be made any larger. Okay, so that has a special role because they in this jargon they are the result of more merging. Okay, or in other words, they are cheaper to implement, right? I mean, they are the cheapest to implement. I cannot expand them anymore. And so now let's look at an example. Let's say I have 3 variables, x, y, z. So I could have a minterm. So let's say x and y and z would be a minterm. Can someone tell me another minterm? Like, for example, it might be x and not y and z, right? Let's say the function was true for both of these combinations, then there would be minterms. Implicant, if I have an x and z, is no longer a minterm, but it may be an implicant because it includes y, both values of y, right? So it's really a combination of two possible minterms. And likewise, if I look at x alone, it's an implicant, possible implicant. But for y and z, it's basically saying y and z can take any value. So x corresponds to x equal to 1, and then y and z taking all the 4 possible values. So that is what we see out here. Implicant x is larger if you view it on the Carnot map or in the cube space, because it has fewer variables. It has only one variable x. Implicant x and z is smaller in terms of number of cubes, number of corners, or number of cells it corresponds to, but it has more terms. So they go in different directions, right? I mean, the more cells I merge, fewer literals I need in the expression. Minterm corresponds to a single cell. So it has the most literals. So most costly to implement, but smaller in the sense it corresponds to a single cell. So minterm, so every minterm is an implicant, but not every implicant is a minterm. Every prime implicant is an implicant, but not every implicant is a prime implicant. So let's talk about it. So this is the same example. So let's look at this red square. Is it a prime implicant? So the thing you have to think is, can I expand it in this Carnot map? Can I merge it with more? I can also create groups of 8, for example, or groups of 16. They go as power of 2. So question is there a group of 8 which includes, so group of 8 might be like, let's say, the top 2 rows. So in this case, obviously not, right? There's just no meaningful way to expand this thing. So it's not a prime, so it is a prime implicant. It can't be made any larger. What about this guy, 5 and 13? So is this a prime implicant? Anyone? Can I make it larger? Can I make it into a group of 4?
No, it cannot be
No,
expanded.
it cannot. So that too is a prime implicant, right? What about this, 1 and 3? Can I make that larger?
Also no.
You can make it larger.
You can make it larger, right? That's the red one.
Wait. Oh,
Right?
yeah.
Yeah,
My
right?
bad.
Okay. So that one is not a prime implicant. Okay. So continuing with it. So now we have seen minterms. Minterms can be merged into implicants. Some of those implicants are prime implicant. They cannot be grown anymore. So now let's talk about another concept, which is called essential prime implicant. Essential prime implicant are prime implicants which are the only one that are containing a particular minterm. So remember, minterm corresponds to places where the function is true. Prime implicants are preferred because they are the largest in terms of whatever entries they cover. But now imagine a prime implicant which is such that one of it covers a minterm, and it's the only prime implicant which covers that minterm. So intuitively, I want prime implicant, and if there's a prime implicant which is the only prime implicant which covers a particular cell, then in any solution, I better have that prime implicant, right? Because if I don't include that prime implicant, then I would be including something, I would be using some implicants which are costlier to implement. So essential prime implicant basically is they are essential to the final solution. So essential prime implicant is the only one containing this thing. So let's take an example. So let's say I have this function, f is a and not d, or not a and d. A, so it's a A and so it's a 4-input function. Okay, A, B, C, D, B and C. A and not D corresponds to this. The first one is A here, and last one is D. No, sorry, I'm sorry. First one is D, and last one is A. D, A. Okay, and not AD is this 1XX0. They are prime implicants because they're the largest possible in this particular example, and they do not share common minterms, so they are both essential. Let's go back to example. So in this example, we had these. So we had, recall we had, in this example, we had 4 prime implicants, right? We had the red one as shown out here, and then we had 3 green ones, right? We had this green one, which is already shown out here. We had this green one, and we had the green one corresponding to this, right? Those were our 3 prime implicants. They cannot be grown anymore. Okay. Now, what I'm interested in finding out is which one of these. So firstly, the red one. Is red one a prime implicant? We saw it was. Is it an essential prime implicant? In other words, does it cover a minterm which is not being covered by any other prime implicant? So is there a cell inside the red one where it's the only prime implicant covering it?
7, right?
So 7, excellent. Do you think there is any other one?
That's it.
1.
1, yeah, 1 also, right? So 1 and 7 are both minterms which are not covered by any of the 4 prime implicants that we have.
Wait, so how is 1? Because isn't like the edge on the right side, like, isn't that covering like 1, 3?
Well, but is 1, 3 a prime implicant? It's not, right? So 1, 3 is not even a prime implicant.
So essential ones only exclude, only include the prime ones, not the regular implicants.
Essential prime implicant have to be a prime implicant. And then, so essential prime implicants are prime implicants, meaning they cannot be grown anymore. And they have the property that they have at least one cell which is not covered by any other prime implicant. So since one of you just asked about the right one, the answer is it's not essential prime implicant because it's not even a prime implicant. Right? Because 1, 3 can be merged into a bigger 1, 3, 5, 7, the red one. Right? So this one is not even a PI. And so if it's not a PI, then obviously it can't be an EPI. Is that clear? Right? I mean, so the trick one out here, right? I mean, EP, for something to be an EPI, essential prime implicant, it has to be a PI first. The middle one, 513. What about that? So you have to ask, is it a prime implicant? And then ask, is it an essential prime implicant? So is it a prime implicant?
Yes.
5 and 13. It is, right? I can't grow it any further. Is it essential?
Yes.
Yes, because of 13, right? 13 is not covered by anything else. Okay, so that one is essential. In the third case, already discussed, so not going. So how to identify essential prime implicants? Well, I guess the trick really is to, I guess visually we can do this thing, but mathematically, if you were to write a piece of software, which actually sort of I did for the AutoGrader, you have to kind of enumerate. Really, kind of, because the definition is essential prime implicant is going to have a minterm which is contained only in that prime implicant. So essentially, it's a messy search iteration problem, right? So you can write an algorithm to do it. Visually, it's easier to sort of do it. But when you're dealing with large problems, you have to iterate over all prime implicants for all minterms within each prime implicant, right? I mean, you have to sort of iterate over that. So kind of the idea is identify all prime implicant. Is there a minterm that is covered only by one prime implicant? If so, that prime implicant is essential. Okay. So
Quick question.
sure.
So is there like, is it guaranteed that like whatever like configuration we come up with, like in terms of like prime implicants like minterm, is always guaranteed to be unique?
Essential set of prime implicants and set of essential prime implicants are unique, other than if you were to shuffle the order of inputs. Okay, so if you shuffle the order of inputs, they may look different, although they're still unique.
Okay.
Okay, so usually what we do is we agree upon a particular way of ordering the inputs, like let's say dictionary order. We can say, we'll always, whenever the input names are given, I will have the sort the inputs by dictionary order. And once you do that, they're unique.
Okay.
Okay. Yeah, great question. So I identify all the prime implicants. There are 4 of them, right? Then so now unfortunately in this example every prime implicant we have is essential. Okay, so it's not a very interesting example. In general, in problems there may be prime implicants which are not essential. So let's look at some examples like that. Possible examples. So let's look at this one. Okay, so here you see these implicants, right? 1, 4, sorry, cell number kind of you see these cells being covered. Okay, if you look at this one, which is 13 and 9, okay, don't worry about what these 0, 4, 8 they mean out here. This is, I just copied it someplace, but the main point I want to do is, and by the way, this X means don't care. Okay, so genuinely the output of the function there is we don't care. You can think of it as a 1 or a 0 as long as you're consistent. So that's why the grouping here that you see, this grouping is saying I'm going to assume that the X in this cell is actually corresponds to 1, because the user doesn't care what the value is. But that's not why I'm showing this. Look at this one. So this is a prime implicant. I cannot draw it anymore, but it's not essential. It's not essential because I can have another prime implicant like this, 8 and 9, and I can have another prime implicant which is 5 and 13. So 13, cell number 13 is covered by 5 and 13, and cell number 9 is covered by 8 and 9, which are also prime implicants. So therefore 13 and 9 is not essential. It's a prime implicant, but it's not essential, because I could imagine selecting 5, 13 and 8, 9, and therefore not needing 13, 9.
Oh, good question. So in this case, like selecting 13, 9 is like the most optimal one, right? Since then you don't have to like have like 2 additional midterms.
Yeah, well, so then comes the issue of which is better, right? Which is more optimal.
Okay, so that's like a different question. It's not really.
Yeah, that's a separate question, right? So essential means that it must exist in any solution, optimum or not, right? I can't imagine a solution where that essential prime implicant will not exist. Okay, as long as I'm using prime. So one thing, hopefully you agree, is that for any solution, I should only use prime implicants. There is no point in using anything which is smaller, which covers a smaller thing, right? So a good solution would have prime implicants only, or prime implicants ORed together. And what this is saying is that if I look at those solutions which are ORing of prime implicants, an essential prime implicant must always appear in such a solution. That's why it's essential. Whereas other prime implicants, I will have to select to minimize to my cost. Okay, so essential, if I identify essential, I can put them aside and say, look, I always need to have those. And now I can worry about the uncovered cells. So for example, in this particular one, if you think about it, 8 and 10 is essential because 10 is only covered by 8 and 10, right? So kind of the shaded one, right? It is essential. So essential is X's or don't cares. Okay, so let's try this example. So these are, this is a Karnaugh map, and what we are now going to do is to play the covering game. So the red ones is where the function is 1, okay? Okay. So I can certainly merge 1, 3, 5, 7. This is the same problem we had before, right? Okay. This is another prime implicant. This is another one. This is another one. Okay. And in this particular case, all of them are essential. All of them are covering at least one cell. So I have 4 prime implicants, and all of them are essential. So if I'm interested in finding if I'm interested in finding things, then I can basically focus on these. So sorry. Okay. So I have these. So the rule, so the intuition then becomes that I should definitely select all the essential prime implicants and then a few more in general. A few more, doing so optimally somehow. Now, in this problem, all prime implicants are essential. Therefore, my solution is trivial. I need to use all 4 of them. So my solution would consist of gates corresponding to these 4 prime implicants. And so then the final step of the problem becomes going from the prime implicants we select such that the collection of those prime implicants cover all the cells which have a value 1 in my function. Then I'm going to go to gates. So my DCBA has these 4 prime implicants, which we saw earlier. I make gates corresponding to each one of them. So like 0xx1 means D is corresponding to not D and A, right? So that's what we have out here. This is not D and A. The middle one is 001x, so it is not D and not C and B, and so on and so forth. And I have 4 of these, so finally I'll have an OR gate. And I can always do a NAND type solution using De Morgan's, right, that we have covered before, but that's kind of the basic structure out here. So I can convert it into a NAND one like this. So this is how a real implementation on the right-hand side, this is how it will look like. So going from left to right is just De Morgan's, right? I put bubbles here and then move the bubble to the input. This guy is nothing but NAND gate. So that's what we do. So this kind of begins to implement stuff there. So the strategy then becomes, given the user's description of the function, create the Karnaugh map, do this covering business, identify all the essential prime implicants. You must use those. From the remaining one, you have to identify some good ones so that every cell with a 1 is covered, and then translate it into gates like this. This is what is called as 2-level logic. It's called 2-level logic because it has 1 stage here and it has a 2nd stage here. We don't think of NOT gates as part of the stage. So this is stage 1, this is stage 2. Okay, NOT we don't worry about because generally we have signals coming in available in both format. Okay, so we kind of ignore that. We basically say that, look, I have to do complement of a signal anyway, so let's not count those in the stages. So yeah, we have covered this point. NAND gates are cheaper. So I'm not going to. Okay, so now let's look at another example. So oftentimes what happens in life is that we are implementing something where for some input combination, I don't care what the output is because I know perhaps that they will never occur, or I genuinely don't care. And sometimes it could be that my input uses more bits because the number of input cases was not a power of 2. So I have some bit combinations which are unspecified. So let's say I am trying to represent decimal numbers, decimal digits, 0 to 9. So 0 to 9, I need 10 combinations. So obviously I can't use 3 bits. I have to use 4 bits, but not all 4 bit combinations are valid, right? Because I only need 10 of those. So when I encode decimal digits into 4 bits, then generally 0 will correspond to all zeros, through 9 will correspond to 1001, and then these I don't care because they correspond, they can never occur because I'm only worried about 0 to 9. So now let's imagine you are implementing a decimal version of that function, 1 or prime. So from digits 0 to 9 are the only ones that will occur. And the function is such that if the input is 1 or input is prime, then the output is 1. So that's what we have, 1, 2, 3, 5, and 7. And for these other cases, don't care because they can never occur because the input is a decimal digit. So this, in terms of our notation, we write as the min terms 1, 2, 3, 5, 7. And then we also write which are the don't care terms, 10, 11, 12, 13, 14, 15, don't care, and we just represent them as a D. So what does don't care mean? Don't care means that for those, if perchance the input 1010 were to occur, I generally don't care because I know that input will never occur. So you can design your system whichever way you feel like, whatever lowers the cost. So I have some freedom now. So you can think of don't care as giving you freedom to optimize the design. So what does it look like in Karnaugh map? Well, in Karnaugh map, no, in a bunch of cells, I have an X. I don't care. I can think of them as a 0 or I can think of them as 1, but I have to make up my mind. Okay, I can't say for the same input, I can't say it could be both 0 and 1. It has to be either 0 or 1, but I have the freedom to pick that. So that freedom can be exploited to simplify merging. So looking at this, and remember our goal is to make big clusters. So what cluster, and remember also clusters have to serve a useful purpose. They should cover at least one cell with a 1. So is there a cluster of 8 which covers a 1? Well, firstly, is there a cluster of 16? Namely, is the whole function 1? Obviously not. Is there a cluster of 8? No. How about cluster of 4? How many cluster of 4s do you see such that they include at least 1 1?
2.
Okay, so tell me which ones.
Like the square, like 1, 3, 5, 7.
Okay.
And
What
then
else?
3, 7, 15, 11.
Okay. Does anyone see anything else?
3, 2, 11, 10.
Excellent, yeah. Okay. So I have three clusters of 4, and between them I have managed to cover all cells which are 1. So I'm done at this point. So what would my expression look like? Well, hopefully I have animation, so let's just walk through them. So let us find all prime implicants. This one, actually, this is another one, right? This one also cannot, so I missed that one. You have this one, and you have this one. So there are 4 of those.
Oh, quick question. What does the second one matter? Because it's just like X's, right?
Well,
Like-
yes, it won't matter because it is the blue one is already covering 5 and 7, but technically it is a prime implicant,
Okay.
right? Okay, so we may not choose it. So the question that you are asking really is, would I need it? No. Okay, but
So it's like not
technically
essential.
technically it is a prime implicant. Yeah.
Okay.
Okay, so I have 4 of these. Let us find all the prime implicants. Now pick the essential ones. These are essential. Only these 2. And actually, right, the other 2 prime implicants are not essential because they are, we can verify, right? The purple one is the ones it is covering, which is 3 and 7 are covered by blue. And the brown one is covering 5 and 7 ones, but those are covered by blue. So the purple one and the brown one are not essential. And the green and blue are essential. But remember one thing, essentials must exist in any solution, but I may still need some of the non-essential ones, right? Not in this problem, but in general. So these are the 2 essential ones. I have to pick them, right? Because otherwise I cannot have a solution. And once I pick them, actually, I'm covering the whole thing anyway. So I'm done. None here, cover any remaining midterm. I don't need that. I'm done. So that's my solution. 0xx1. What does 0xx1 correspond to? This is not D and A. And this one is not C and B. So the whole thing is ORing of the 2. So I'll have, so that's what it corresponds to. Okay, so that messy looking thing actually boils down to 2 2-input AND gate and 1 2-input OR gate. Okay, so super simplified. So that's what our solution looks like in terms of an AND gates. And okay, yeah. So again, just remember, this 2 is an AND gate by De Morgan's. Okay, how about 5-input functions? Could I generalize Karnaugh map to 5 inputs? People stretch Karnaugh maps to 7 or 8 inputs, and that's where kind of things begin to break down. So 5 inputs we can, because what we can do is I can draw 2 Karnaugh maps. So 5 inputs would be, let's say, A, B, C, D, E. So what I can do is I can draw 1 Karnaugh map for equal to 0 and another Karnaugh map equal to 1. And then neighboring relationship would also exist between 2. Think of them like 2 layers. Okay, so that's kind of the idea. So 5-bit Karnaugh map will look something like this. I will, for E equal to 0 or equal to 1, and then you can say a cell 3 here is neighboring to the cell 3 in the other map, right? We can go kind of, you know, in a different dimension, okay, right, in the E dimension. So I could do that. So imagine stacking these 2 tables kind of in the E dimension, okay? And so 5 and 5 are neighbors, okay? So that's how it works. Any limitations of Karnaugh maps, okay? So let's talk about those.
Just a question.
Yeah, go ahead, please.
In the course, are we ever gonna make? Are we gonna ever? What is it? Work through a 5-bit Karnaugh map, or are we gonna use some other methods?
Oh, I'll ask you to do 10 bits Karnaugh map. You're talking about only 5?
Yeah.
No,
Okay.
but I think 5 is doable, but beyond that, yeah, I think 5 or even 6 is doable. Beyond that is not. Okay, so I would again like to emphasize, look, Karnaugh map is more of a teaching aid at this point. It is not how you do things in real life.
Okay.
Okay. Will I ask questions? Yes, because I'm required to ask you, because it's part of archaic engineering curriculum that an entity called ABIT insists that we teach you. Every university therefore teaches it, but practically speaking, in real life, you are not going to be using Karnaugh maps. Okay, so I will ask you 4 or 5, no more. Okay. Okay. Sorry about the screwed up animation note here. Okay, so what's the limitation of Karnaugh map? The main limitation of Karnaugh map is that it is good if you are designing two-level logic, and or and those kind of things. It results in, it lets you optimize how many literals you need. But two-level logic, which is sum of product or product of sum, is not the only way you implement things. I can have deeper logic where there are where it's possible that I may have terms which go multi-levels possible. So oftentimes what happens is that, when you can, whatever Karnaugh map yields, you can further simplify if you are willing to go more than 2 stages of logic. So, but two-level optimization is how things first started out. And until mid-80s, late 80s, that was pretty much the norm. Even there's a very famous tool called Espresso, came out of UC Berkeley, and it really nailed it in the sense that it had very good algorithms and all to do it. And actually, there's a Python package called PyEDA, okay, which actually we use in our autograder, which actually lets you do these kind of things. You can draw truth tables and stuff like that there and optimize expressions and all there. So if you are interested in sort of using that in your, when you solve the homework, be my guest. Okay, but it's for 2 level, right? One final stage and one middle stage. And that was great because a lot of early chips were designed like that. They were designed as 2-level logic. But starting late 80s, 90s, and certainly nowadays, we are no longer limited to that. So I can have like logic which has many, many levels of deep. I may have like many stages of gates in there. So you can think about like depth of a circuit. This is, if I ignore the NOT gates, this is a depth 2. But I can easily imagine some circuit like this, let's say. Something like that, right? I mean, in that case, I have 3 depth, right? So I can make deeper circuits, and sometimes they are cheaper. Often they are cheaper, faster, smaller. So Karnaugh map doesn't work there. You need other kind of techniques. You need the kind of techniques that we use when we do algebraic manipulation. So that's the limitation of Karnaugh map. So this is an example. I can take this expression and I can factor it like this. So now you can see that I need more levels, right? I have a AND level, then OR, then finally another AND. So there are many possible ways to factor it, and how to do this general problem, if I am willing to say not limited to two level, is what is called as an NP complete problem. It's a hard problem, okay? Even harder than the Karnaugh map problem. Karnaugh map problem is hard itself. It's also NP complete, but this more general problem is even harder. Okay, so that's the main. So that's Karnaugh maps. So Karnaugh map, as we saw, give us solutions which are sum of products, right? That's what K-map thus far we saw, right? We created these clusters of ones, and then we ORed them together, right? So each cluster corresponded to an AND term, and then we were ORing them together. But we saw also last time, or I guess the lecture before that, that just like we have DNF, we also have CNF, disjunctive and conjunctive normal form. So I can do the whole story that we have been doing, where instead of focusing on ones, I can focus on zeros and cluster zeros. And if I do that approach, I will get product of sum. I will get expressions like A or B and not A or B or something like that, right? I mean, I'm going to get product of sums. This is a product. And that's the parallel world. And if you spend time thinking about it, you could always do it. I'm going to show it quickly because the underlying sort of principles are exactly the same. So two types of implementations. Sum of product, which we saw thus far, focuses on one entries which are one. Product of sums focuses on inputs where the truth table takes a value 0. So looking, and remember I talked about how, like, whether there are fewer max terms or fewer min terms, what is better. So let's say I had this function. Then clearly it has only two places where there is a 0. So maybe my solution would be easier to perform if I focused on the zeros. So f is 0 when DCBA is 1101. That's row number 13. Max term 13. Or when DCBA is 111. Looking at this, do you see a merging opportunity? So f is 0 when DCBA is 1101 or when DCBA is 1111. Is there any variable which doesn't matter? Can I merge these two cases?
11x1 where B doesn't matter?
Yeah, 11x1 because B doesn't matter, right? So I can play that game. So now let's walk through this thing. So if DCBA, if f is 0 when DCBA is 1101 or when DCBA is 1111, then I can say f is 1 when DCBA is not 1101 and DCBA is not 1111, right? Logically the same thing. Does everyone agree, right? The first statement, f is 0 when either condition 1 or condition 2 is met. That is the same as saying f is 1 when neither condition 1 nor condition 2 is met. So I can write it like this by focusing on the zeros. And that's kind of the idea that for some things, product of some implementations would be a lot easier. So how can I do, so these are the max terms if you recognize from all, right? These are max term is made of ORs. So that's the intuition that for some problems, well, firstly, hopefully for half the problems, it's better to do with max term and half the problem is better to do with min term, right? Probably the world doesn't have any bias towards 1 or 0, right? So assuming all functions are equally likely to occur in our lives, we would expect half the time we would prefer max term, half the time we would prefer min term, or maybe there is a middle where we could go either way. Okay, so how do we work this thing out? So Karnaugh map for product sums. So this is our Karnaugh map for this function. So I could play the game of 1, but there are a lot of clusters out here, and this is an example where you can see there's a cluster of 8. There is another cluster of 8, and there is a third cluster of 8. So this problem is pretty nice because I can solve it with 3 clusters of 8. So it's not too bad if you were to do it with ones. But what about if I were to attempt to do it with focusing on zeros? So the first step would be we focus on zeros. So now I'm going to create clusters of 0. So this cluster, and we are done. So one cluster of 0. This one, we are going to now write it as 1, 1, x1. Okay, so C and D are 1, 1. And B doesn't matter, so that's an X, and A is 1. So that's 1, 1, X1. But that doesn't work for us because remember, we are thinking about max term cases. So we are not going to write it like this. We are actually going to flip it. We are going to write it as 0, 0, X0. So this is very important part. If you recall, when we were doing max term, if there was a 0, then the literal appeared positively. And if there was a 1, literal appeared negatively. So that's a super important part. If D is 1, then that means really I'm interested in the 0 out here. Sorry. I don't know how to clear this thing here. Okay. Okay. So, when we are, so the game, when we were dealing with ones, we were writing it as 1, 1, X1 and all, right? I mean, we were looking at the values 1, 1, and 1. Here we are going to flip it. So the row is 1, 1, so we are going to write 0, 0. And for the column, B doesn't matter, A is 1, so we are going to write A equal to 0. So that's what we have out here. This. So this is D, C, A. And then I'm going to be ORing them together. Remember, it's a max term. So OR of 0, 0, X0 is the zeros now correspond to not D, not C, not A. So that's the term we are going to get. So depends on how you kind of like to think about it. One way you can think about it is I'm going to write it like this, 1, 1, X1, but when I'm ORing it, I'm going to put a negation there. Or you can write it as 0, 0, X0. So that's what we end up with. That's our expression. Actually, this one is interesting. This is both DNF and CNF. This is both product of sum and sum of products. It is, we went out doing product of sum, so it is product of sum, but it just so happens it has a single term in it, so there is no product. But I can also think of it as sum of products because I'm summing three terms. Okay, those were the 3 clusters of 8. So it so happens in this problem, the POS solution and SOP solution look the same. But that's kind of the basic idea that I'm going to form clusters. Each cluster will correspond to an OR, and I'm going to then AND them together. Yeah, I'm not. This is just explaining max term. So let's look at another example. So this is our decimal primer 1. We have seen this one before, but this time around, I'm going to focus on the zeros. So I'm going to create clusters of 0. So I can make a cluster of 0 here. There's a cluster of size 8. Any other cluster of 0? What's the next cluster of 0 we'll go after? Well, we again are interested in big clusters. So let's try that. I can create a cluster of 4 like that. And that one would be OR of X0, X1. And then again, you would see, like, for example, D changes, so that's an X. C is 1, that's why we put a 0 here. B changes between first and last column, so that's an X. And A is 0, which is why we put a 1 out here, we flip. And then we need this one, that's a third one. And together with that, we have covered all the zeros while making use of X's. So those are the terms. And then that's the circuit. Okay. This term doesn't need a gate because there's a single input. Whereas the other 2 need OR gates. So that's the solution I end up with, which is what this guy looks like. So I forgot what the solution was with the product of sums, sum of products, but this is an alternative one to do it. So this is product of sum, and this is sum of product. Which one do you think is better?
Sum of product.
Yeah, so if I already have inverters available, then sum of product needs 3 2-input gates, whereas product of sum needs 2 2-input gates and a 3-input gates. If I count the inverters, then I need one less inverter on POS. So one way to estimate cost is you add the total number of inputs in the gates. So 1, 2, 3, 4, 5, 6, 7, 8. So that would make it 8. And the other one is 1, 2, 3, 4, 5, 6, 7, 8. 8. So if I did not have inverter available, then both are equal. If I had inverted signals already available, then SOP is better. But I guess the main thing is these expressions are equivalent. And you can verify it. You can go from one to other using algebraic operations and all. They look very different, but they're the same. Okay, so I could do all of this by focusing on zeros, but there's an alternative strategy which you might find easier. So if someone asks you to do product of sum, then you'll say, okay, I'm going to focus on zeros. But alternatively, we can make use of that whole dual function business and all. So kind of the idea is we can flip F. I can just complement the whole Carnot map. So wherever there was a 1, I'll put it a 0. Wherever there was a 0, I'll put a 1. Wherever there was X, I leave it as an X. So this is my new Carnot map. And now I can focus on ones. So now using Carnot map, I will come up with a sum of product expression for not F. Okay, using what we did earlier today. So I'll focus on this. That's the largest cluster. 1, 1, X1. That gives me not F is A and C and D. And now I complement. So take the complement. So F is not of not F, which is not of A and C and D. And then I apply De Morgan's. That becomes not A or not C or not D, which is what we got earlier. I find it easier to do this way. I guess mentally I find it easier to think about ones, but really they're just two different ways of looking at the same thing. Whatever works for you, just use it. Okay, let's look another example. So here there's a 0 at 9 also. So I create two OR terms. They cover everything. So 0 when DCBA is 1, 1, X1, or which is OR 0, 0, X0, and this is 0 when DCBA is OR. And that's the expression. Or I can do it with that flip approach. You will get the same answer. So strategy 1, then we convert to gates. So that's the gate expression. We have seen this thing. Strategy 2, complement, and then apply the complement thing. I'm going to go through this rapidly because we have seen it earlier. We'll get this kind of expression. Not F is this, take the complement, F is this, and that's what we get. You basically get the same answer. Okay, whichever way you do. Okay, so you should also in the P set you would see that we asked you to work with Carnot maps to sort of look at these problems, this type of problems. You'll see problems like I will give you, there is a function which corresponds to this, M17, which is another way of saying that I'm just telling you what rows of the truth table or what cells of the kernel map the function is one, or we may give you the kernel map. And then we may ask you to implement it as a good product of sum, minimal product of sum. That means you have to minimize the number of literals in your final solution. So let's look at this. So 1 and 7. Okay, so firstly, when you're faced with this thing, you should immediately ask, what order should I consider the inputs? So in this particular case, we are really looking at the order CBA. Okay, so the cell corresponding to 001 would have a 1, and the cell corresponding to 111 would have a 1. So we'll have a 1 here and a 1 here, and then the rest are 0. So, and we want product of sum. So product of sum should immediately say, look, I'm going to focus on the zeros. So I have one term like this. That's x0, right? It's x because C doesn't matter, B doesn't matter, and right, and A is 0. I look at this term, 01x. I look at this term, that would be 10x, and then so that's my overall thing, and then we are going to combine them together. Okay, so anyway, that's kind of the idea. Now, in this approach, what we are really focusing on is optimizing for cost as in size. In real life, often there are other considerations that kick in, which may lead you to solutions where I may include additional min terms or max terms, additional gates in order to achieve some other property, like a design which is lower in power consumption, or which is more robust, or faster, or something like that. Okay, so, and not just focus on how many literals I have. So the literals, like I said, correspond to silicon area somehow, but maybe we may have other criteria. So I want to talk a little bit about one such consideration that often creates, leads us to a different consideration. So let's look at this digital function. So it's a 3-input digital function and output f, and it looks like what is shown out here. So let's say A, B, and C are as such. A is held at 1, B is held at 1. So we are always in the column 1, 1, so this column. And C starts out at 1, and at t equal to 1, C goes to 0, right? So A, B, C are coming from the outside world, and let's say C switches from 1 to 0 like this. So what do we want F to be? Well, since A and B are 1, 1, so what do you think F, what would be, what should happen to F in this case? Anyone? What would be F before t equal to 1, and what would be F after t equal to 1?
Wait, could you explain the inputs again? I didn't get like how you're like, yeah, I just didn't get what you were asking with the inputs.
Oh, so this is just a diagram of what A looks like over time, B looks like over time, and C looks like over time.
Okay,
just coming
got it.
from outside, right?
Okay, yeah.
So A and B are held constant at 1, and C is changed from 1 to 0 at time t equal to 1. My question is, what do you think will happen to F looking at this table?
I think it will remain true.
So, and it will remain at what value?
As
F
1.
is 1, right? So this thing is suggesting that F equal to 1 throughout. That's what we intuitively seem to be suggesting. But let's see if that happens. So that's what we are thinking. But let's say it happens. So now let's say I gave you this kernel map, and I asked you implement it. Well, what would you do? You will make a cluster out of that, and you'll make a cluster out of that. That's what seems right. So one says A and C, the other says B and not C. I will make the gates. It will look like this, right? The bottom gate is B and not C, and the upper gate is A and C, and then we are ORing them together. So that's the real circuit looks like. Now, real circuits don't work instantaneously. They have some delays in them, right? So let's say the AND gate and the OR gates had a gate delay of 1. They take the signal, the output changes 1 time unit after the input. And let's say my inverter was very slow. It took 3 time units. Sometimes that does happen because sometimes the output of inverters may be going to other places also. So they may be seeing a lot of wiring capacitance and therefore may just be slower. So let's say that's the case. Now let's see what our timing diagram looks like. Okay. So C changed from 1 to 0 at t equal to 1. I've kind of drawn it in kind of not vertically, the arrow, the edge out here, this one, just because in real life, signals don't change from 0 to 1 instantaneously. In real life, signals take a little bit of a time to rise or fall. Okay, so that's what we have. Now let's look at what would Cn look like, which is the output of the inverter. Well, it is 3 time units delayed. So while C started changing at 1, Cn will change at t equal to 4 in the opposite direction. So Cn will look like this, as shown out here. Now let's look at D. D is being affected by A and C, and C changes at t equal to 1. So when do you think will D change? So if C changed at t equal to 1, then D will change at t equal to 2. Right? So D will look like this. D will start out as 1 because A and C were both 1. But when C became 0, then after 1 time unit, D becomes 0. So D looks like the signal that is shown out here. Now let's look at E. So when we start out, E is seeing B equal to 1 and Cn equal to 0, right? Cn is 0, B equal to 1. So when we start out, E is 0. But then when Cn changes, E will change. So E will look like this. 1 time unit after Cn changes, E changes. So E becomes 1. Now finally look at what will happen to F. So F starts out as 1, but F is combining D and E. And as you can see, that there is a time when D and E are both 0 because of these delays. And at that time, F will get the value 0 because it's an OR gate. So F will look like this. So what we thought was going to happen is F will remain 1 throughout. Because of these delays, F is seeing this kind of dip for a little bit. Very tiny in time, but nevertheless, there is a dip, a glitch, or what we often call as hazard. And now you may say, okay, why do I care? It's just a tiny glitch. In reality, unfortunately, remember, this could be a signal going someplace, and they may be looking at the edges. We already saw sequential circuit look at edges. Besides that, these glitches also consume power because when there is a glitch happening, capacitors have to be charged and discharged. So they consume power. It makes your circuit less green. So hazards are risky and hazards are inefficient. So we need to avoid hazards. We don't want to make sure. In this case, because we wanted F to be 1 throughout, could I make F 1 throughout? What would you do? So firstly, do you understand the problem? Because of these delays, f is not behaving in that idealized manner that we thought it would. F is no longer 1 throughout, but if I examine at a fine time scale, I see that f has this hazard. Can you think of something that I can do to solve this problem?
Could you like also implement like the delay on the other side? On the
Okay,
other
I
end?
could. You could. Unfortunately, it's very hard to design circuits which have precise delays. It's almost impossibly hard. Okay, so you might think, well, the thing is the following, that the delay of a circuit depends upon lots of complicated things, temperature and stuff like that. So while in principle you are right, one could, if one could. In practice, we just can't design circuits with predictable delays which are very precisely predictable. So eliminating with that approach is not easy. So what we will do out here is the following. The challenge that is happening is that we were originally at 1, 1, 1, 1. So we were originally in this cell, and therefore covered by A and not C. And then later on, we are moving to 0, 1, 1, right? C 0, 1, 1. So we are moving out here. So the OR gate is input switching from 1, 0 to 0, 1, right? I mean, before, when we start out, one input number D is high, and later on input number E is high, but D and E are not changing together. So what we want to make sure is that in that middle zone, also OR gate sees a high input. So what we are going to do is we are going to create a third input to the OR gate. And that we do by also including this implicant. So kind of the idea is that as C is changing, we will always have one of the inputs to be high. And the reason I bring this up is that now, as you can see, the green one was not necessary for functionality earlier if we didn't care about these glitches and all, right? Because the circuit worked correctly at t equal to 0 and would be work correctly much after t equal to 1. The problem was in the middle. And so sometimes we may include extra implicants to avoid problems like these hazards. Okay, so this was just kind of a side story of sorts, but optimizing for area is not the only goal. We are trying to create circuits which are robust, and also we're not going to spend much time on that issue in this course, but just wanted to bring to your attention that there is never a singular objective, right? I mean, we want area, but we also want robustness, and we want low power, and we want high speed and whatnot. And so sometimes we have to deviate from what the naive application of Karnaugh map might suggest to us. So that's what's happening out here. There's an extra hand turn, and that gets rich of this type of hazard. And if you work with a new circuit, you will just see that F will remain flat out as it is. Okay, so we are at the end of the lecture. So we saw lots of things in this module. We saw different ways of representing functions. We saw concepts like prime implicant, essential prime implicant. We are also going to see in the P-sets and quizzes and all additional concepts around these that I will have you explore. Karnaugh map is a good strategy to do stuff manually, but nowadays you can also use lots of tools. And again, I thoroughly encourage you to discover and use whatever tool. Or one thing I would just like to suggest is the following: if you decide to use a tool like ChatGPT, it is often wrong. Okay, so in fact, we even ask a question in P-set about this thing. So be super careful when you are using language models and all, because of course we will not accept the excuse ChatGPT set. So tools which are specifically designed for logic manipulation, they use algorithms as opposed to language models. So they are obviously accurate, and so I would suggest using those. The cheapest, easiest ones I can suggest to you is Wolfram Alpha. It has good capabilities, or using a package like PyEDA. Okay, it's pretty easy to use in case you want to do it. But the problems that we are going to be asking you, you can do it by hand, or worst case, writing little snippets of Python code yourself to do it. This Karnaugh map approach is kind of painful for more than 4, 5, 6 variables. So in the good old days, there was a method called Quinn-McCluskey method. I am not covering that in the course, which would enumerate all the minterms and go through it. Basically, it has been overshadowed by the modern algorithms. So, and if you are interested in those algorithms, there are graduate level courses which cover those type of stuff. I don't teach them. It's not my area of research, but both faculty in CS and EC cover those kind of things. In real life, software tools do the optimization. And so you are really controlling the tools and making sure they produce the right thing. But a lot of drudgery is just taken care of. And then these issues like hazards, which create problems for the circuit and all, produce extra constraints. So we don't just blindly chase area in real life. We chase a good design, a design which will work under lots of different conditions, and a design which would be, like I said, small in area, fast in speed, and robust and low in power consumption, right? We kind of want everything. Of course, nothing. There are always trade-offs, and therefore sort of modern algorithms kind of let you work with those. So with that, we are done with this. Next topic that we are going to cover, and we are pretty much right on the time, is going to be looking at how do we compose these things that we have seen into more complicated combinational functions. We'll do that on Wednesday, but what I would also like to do, because I want to hand out a design assignment, is to spend some time on Logisem. Now, normally, Logisem stuff we would have covered out of band. So I'm going to do the same thing. I'm going to record a lecture on Logisem, but I'm going to announce it when I'm recording. So if any of you want to join live, you are more than welcome to. But it's more like how to use Logisem. Okay, it's not. I don't like to use lectures for those kind of material because they are really something. The reason I do it is because I know a lot of students don't bother to look at the documentation and the man pages, so I think it just becomes easy that way. So I'm probably going to do it maybe on Thursday or Friday sometime, so that then we can hand out the design assignment also. But with that, I'm going to stop. So any questions before I stop? Okay, so
Quick.
sure, please.
So for the last topic you covered with like just going from like product to sum versus like sum to product, am I able to just like take the last step of the product to sum and then go to sum to product if I like notice like one is easier? That makes sense.
Usually we will, so it depends. You can usually
Okay.
do it at the last step. You can try it both ways. Oftentimes we will force your hand. We'll say we want product of sum.
Okay.
Okay. So it kind of depends. There's no one right answer to these things. In real life, all you care about is meeting your objectives. So it's only in academic settings where we want to test, can you do sum of product? Can you do product of sum? But in real life, the goal is not one or the other. Okay. So goal is a good design.
Okay. Thanks.
Okay, so I will. I had the office hours last Friday, but no one came. But I'm assuming this week many of you will come because the problem set would be due. I can also hold an additional office hour on Sunday because the problem set is due on Monday. So if that helps, I'll probably do that. Just so that you will have something to work sort of. But otherwise, make use of Piazza. We try to be responsive on Piazza and do start early because it's the problem set is not hard, But if you do it at the last moment, then you will have issues. So, okay. If nothing else, I'm going to stop the Zoom recording and see you guys on Wednesday.